Hello everyone. Today's video we're going to talk about the ideal gas law. In particular, we're not trying to define ideal gases, but we do want to, if you're taking chemistry, we want to avoid some of the things that you might have seen in chemistry. We want to do it the physics way. I am going to try to make sure that if you've seen it one way, you'll be able to use that way and everything makes sense. Now, obviously, some of you haven't taken chemistry, so you have no idea what I'm talking about. Ideal gases are models for actual gases. They're ways of modeling air, modeling things that are not liquids and not solids. And sometimes we take this model and we apply it where it doesn't apply. Like I've put ideal gases on a liquid because you can do things in bad ways. It's okay as long as you know what you're doing. So you're going to see some of this obviously in other places, wherever you happen to see it. Especially if you want to go into medicine, you learn ideal gas law so you can learn things like how the body exchanges gases from blood to lungs or from blood to cells, and all the different ways gases move around the body if they need to as you breathe, as as biological processes go on, and so things like anesthesia. How do you make that work? Of course, engineers are going to need to know ideal gas law for building structures that can withstand pressure and temperature changes. Anyway, part of this is we're looking at the behavior of pressure, volume, and temperature in a thing. Now, before we go and talk about a whole bunch of equations, we're going to define some other things. We're going to find units because in physics, we tend to talk about the individual molecule or the individual atom. And in chemistry, you talk about moles of a gas. And in other things, you talk, well, really what I care about is how many cubic meters or how many gallons or whatever, whatever units you want to pick up. So we're going to define moles. So lowercase n here is n over a constant. So this is molecules. And this down here is Avogadro's number. 6.02. Where is it? Not sure if it's how around that. Because I always use 6 times 10 to the 23. And this is a counting thing. It has no particles per mole. So the idea is that 1 mole has Avogadro's number of particles. There's other ways of defining it. All right. You probably have also seen the number of moles is the mass of a particular particle, a particular molecule, divided by the total mass of the stuff. All right. So, if you're measuring out a chemical, say you're measuring out salt, each salt molecule has the mass of the sodium and the mass of the chlorine atom. But you're going to measure out whole grams of the thing. All right, so it's a way, the idea is that moles are a way of counting molecules. All right, so that's where we're going to go with this, is we want to very carefully work out using moles and counting the number of molecules, everything else that we're going to do. I should be clear that this is the molar mass. All right, so this is a thing as like grams per mole. And then this is going to be the thing that is in, so particle mass. And so you'll see things that look like that. Anyway, I'm just taking us straight out of section 19.5. All right, so that's kind of the preliminary stuff. Anyway, the way you generally see this topic introduced in chemistry is to consider, let's say I have a container and I have a piston inside of it. All right, so, and then I have a gas. So this thing will have some change in volume, let's say. And we can ask, well, what happens to the gas? So maybe there's a change in temperature. And certainly there'll be a change in pressure because that's what you're doing to force the piston downwards. So there's ways of relating this. You can do this experiment where you're going to keep the temperature constant. And so that means that the pressure initial times the volume initial equals the pressure final times the volume final. So this has some law that you've probably learned in your chemistry classes like Boyle's law or Charles's law. I'm going to list all three of these if you've heard those before. If you haven't, you're going to see it the other way around. So this is if T is constant, so delta T is 0. So maybe delta T is not 0. Maybe what you do instead is you put a fire under this and don't change the volume. So if V constant, let's get the eraser out if I can. Actually, let's not. So if the volume is constant, then the initial pressure divided by temperature, that ratio is a constant. So it'll equal the pressure divided by temperature finally. And then there's a version of this that is, well, let's say we don't change the pressure. We don't apply any force to this thing. We let it move. So what we're doing is letting the gas expand as it heats up. So maybe the volume is constant. And so the initial volume looks like the final volume. And so this is if pressure is constant. So delta V is 0 here and delta P is 0. And so the other assumption is that the number of molecules is constant. All right, and so each of these have some name in your chemistry class. I remember Boyle's law and Charles's law, but not which one is which. And there's probably a third one. But ultimately, we can combine all those together. And we're going to get that the pressure and volume over the temperature is a constant. Right. So you could certainly use this, and that's all you would need to know for some problems. So for problems like, let's say, I absentmindedly set a can of soda on a hot stove, which is not unbelievable. I have a wood stove at home. Actually, it's a coal burning stove. and it burns hotter than anything I can think of. It burns fairly hot. And a can of Coke, right? So we need to probably define some units here. So there's my poor drawings. Fire and Coke, have a stove. The idea is that the Coke starts out, when you can it, it has some initial pressure. Say 5 atmospheres. Right. So we're going to, off to the side here, define some units. We define Pascal. Right. So we have, then we had 1 atmosphere is 10 to the 5 Pascal. It's like 1.013 times 10 to the 5. So, you can look that up. By the way, if you're looking up units, there's the front of the book has the physical constants, and the very back of the book has your unit conversions. And so all this stuff is there. You can look up an atmosphere is 1.013 times 10 to the 5 newtons per meter squared. Pascal. Right. So you'll have units like for the volume, 1 meter cubed, and then 1 liter is 0. Volume. 1 liter is 1,000 centimeters cubed. 1 meter cubed is 10 to the 6 centimeters cubed. So 0.001 meter cubed is 1,000 centimeters cubed, right? And then your temperature is always in Kelvin, not degrees Celsius. You have to use in Kelvin because we're always going to talk about absolute temperatures, not changes in temperatures. So, so back to the problem, our initial pressure is, say, 5 atmospheres, and our volume is half a liter, and our temperature is going to be something like canned in a factory, let's say 300 Kelvin. So these are our initial temperatures. Right. So what I'm going to do is get the eraser out, and all this stuff I wrote over here I'm going to erase. I want to keep the rest of it. All right, so whee. So we're going to go and convert all this stuff I wrote down, initial numbers, to their proper units. But we can ask, well, what happens when I set this thing on the stove and it heats up? And let's say the can heats up to roughly the temperature of the fire, which will be, the top surface of the stove. So let's say that that's 1,000 Kelvin. So maybe it's not, but that's, we're going to heat this thing up so it's real nice and hot. Now the volume is going to be the same, is 0.5 liters, and that is 0.0005 meters cubed. This is the thing. This demonstration is to tell you how to convert your units. We want to figure out what the pressure is. This 5 atmospheres is 5 times 10 to the 5 Pascal. And then we're going to leave our temperature here the same. So when we're going to set this problem up, we're going to have pressure initial, volume initial over temperature initial is pressure final, volume final over temperature final. All right. And so the pressure and the temperature change, the volume doesn't. It's a fixed because it's the size of the can. So we're going to cancel those out. And our units here, we're going to stick with meters cubed and Kelvin. And what we'll get is a final, we're going to stick with Pascal and Kelvin. And we'll get, so in this case, we're going to rearrange this to solve for the final temperature. Final is initial, and then we have temperature final over temperature initial. If you do the algebra on this relation, you get this one down here. Well, that's 5 times 10 to the 5 Pascal times 1,000 Kelvin over 300 Kelvin. So this will be 5 times 10 to the 8 divided by 3. So it'll be 1.67 times 10 to the 5, 6. 10. Never mind. Maybe I've done this wrong. Let me go back and do it. 10 divided by 3 times 5 times 10 to the 5 is 1.67 times 10 to the 6 Pascal. You work that out finally. And then you can convert that 16.7 atmospheres. Now, for a problem like this, where what this is a setting up of ratios. Right? You have an initial state and a final state, and you're trying to solve for something about the final state based on the initial state. That's a ratio problem. So when we do that, as long as your units are consistent and your temperatures in Kelvin, you can deal with it. Right? So in chemistry, you probably went and dealt with atmospheres and liters, and that's okay. You can do that. But in physics, we tend to go and deal with meters cubed and Pascal and Kelvin. And there's a reason for that. All right, so we had this relationship, PV over T is a constant. Now, this also has to be related to the number of particles in some way, or the number of moles of a gas and a constant. And so this is where you get the form of the equation that you sometimes see. PV is nRT. Right? So this is the molar form, we'll call it. R here is the gas constant, and it is 8.314 joules per Kelvin mole. Right. That's the chemistry form, and so this counts number of moles. Right. So we can convert that. We can convert it to do numbers of molecules, right? Because N is number of molecules over Avogadro's number. Right? So we can convert that. We can say that the pressure times volume is, well, we'll have some new constant, but we'll have the number of molecules times this K. I'll put a little b there for reason a moment, times the temperature. So this K sub b is what we call Boltzmann's constant. And I'll often call this K. All right, so they're interchangeable in a sense. This is a constant. You can look it up. It is 1.38 times 10 to the minus 23 joules per Kelvin. It comes up in a few other contexts, so that's why we introduce it like this, that it's, the point of it is that we're talking about the number of molecules. But what this ends up being is the way we convert between these two, we're taking the number of moles, substituting in what the number of moles is, and then so K for Boltzmann is R over Avogadro's number. R over N sub A. You can't see that. Why is it going off the screen? All right, so K sub B is R over N sub A. All right. Boltzmann's constant on the left is the gas constant divided by Avogadro's number. So that means we have um, a formula that doesn't deal with ratios. We can deal with absolutes. We can count the number of particles in a gas if we want, and we can do work on problems. Now, the example in your textbook absolutely deals with ratio problems. Right? And it's effectively the problem I did, just with more complex numbers. And it lets you talk about that sort of stuff. Okay. So this isn't too bad. Right? The idea is generally what you're expected to do is more problems like the ratio problems. Right? So that's kind of the important takeaway generally. But sometimes you need to find the number of molecules or something or whatever. And this does one other thing: is anytime you see in KT in a formula, you can convert it to pressure times volume, or nRT. Sorry, that's all right, lowercase. Anytime you see the temperature on one side of an equation, you can probably replace it with some relationship that has pressure and volume in it. And that's kind of important for what we're going to do next. All right. So we're going, this is chapter 21 coming up. And the idea is to talk about kinetic theory, is to say that something is going on with gases that cause them to act the way they are. Now, honestly, to the details, you should follow in the textbook. But the idea is, where does the pressure in a gas come from? Well, there are particles moving around. They have different velocities. All right. And so I've only drawn 4 particles here so far. But let's draw a 5th one in here, and it is moving directly downwards. The pressure is felt on the outside of the container, and it's because gas particles will bounce off of it, and then so they'll reflect upwards again. They'll go. Now, particles that interact with each other, they just interact with each other. They provide pressure to push particles out towards the container wall. But the way you feel the pressure is from the container, and that's the forces of particles interacting with the container. So what's going on here is that the forces on the container are proportional to the velocity squared. The book goes through and does the details on this. Basically, there's a rate at which the collisions occur, which is based on the particle crossing the box a couple of times. Right? Assume a single particle can cross the box. The minimum time it takes to cross is twice the size of the box divided by its velocity. So that means that the pressure, and I should be clear that this is the velocity, is proportional to the velocity squared, and the pressure is forced by area. So the pressure depends on area, and effectively this is the size of the box cubed. So this is really the volume. So you can go through and look at what's going on, and eventually you derive that this pressure is going to be related to the kinetic energy, since it's related to the velocity of the particles. And so you'll get an expression that looks like 1/2 the mass of the particles times some velocity squared is And this is an average now. It is not a vector. It's an average symbol. 3/2 Boltzmann's constant times the temperature. And the point of this is that temperature is a measure of kinetic energy. All right. That's the important bit to take away from this. The temperature is a measure of kinetic energy. So the gist of this, the things that I kind of want you to take out of dealing with the kinetic energy of a gas, you kind of have three sorts of equations. So a per particle average kinetic energy is 3/2 Boltzmann's constant times the temperature. Now, what's going on here is we say that there's an average here because you can make this chart that is the frequency, the number of particles you see with a particular velocity. And this chart is going to have, let's see, let me find where this chart is. There's a reason why I wanted you to see a chunk of this chapter. This is on page 602. This might look like that. It has to be zero at zero velocity. You don't see particles that aren't moving. But this is not a nice bell curve. It has a long tail towards high velocity. And the other thing that you have here is, let's put in red here, a higher temperature has a different shape. So I need to be careful of this. This is 300 Kelvin. This is, say, 900 Kelvin. The higher temperature has a flatter shape. It has a higher average. In this case, what we'll say is the average is the peak here. This is what we're going to call the RMS. RMS is root mean square, which is the square root of the average of v squared for all the particles. So that's not exactly what it is. You can see that it's a little bit off, but in the purposes of these curves, it's fine. But the gist of it is, you're going to see these measures of the average shift towards higher velocity as you heat the gas up. And you're going to see more particles reach a higher and higher and higher velocity. And that's what's captured here, is the kinetic energy is the velocity, in a sense. It's a measure of the velocity. Right? It is 1/2 the mass of the particle times v squared. So these are average numbers. So that's an average velocity. But the gist of it is the average kinetic energy per particle is a function of the temperature. If you heat it up, particles go faster. The total energy of a gas is 3/2 the total number of particles times Boltzmann's constant times the temperature. And anytime you see NKT, you can replace it with pressure and volume. So these are kind of one equation plug and chugs. But I do want to go back and introduce one more equation, and that is, well, how do I know what this velocity is? Well, that's coming from take the kinetic energy is a function of temperature and solve for what that function of temperature is. And what you get is a square root 3. And you can do a little bit of math with this. All right, this is a plug and chug equation. If you get the right parts, you can plug and chug with it. But if I wanted to get the proper, I could rearrange this in terms of molar mass and pressure and volume, right? This Boltzmann's constant times temperature here is really 3 pressure volume over the mass of the particles times the number of particles. And that is the molar mass, is it not? No, it's the total mass. So if you know the mass of your gas and the pressure and volume, you can figure out the average speed. So, the point of this is that there's certain manipulations that are easy to make that will help you with some problems. Like in problems, it's hard to measure Boltzmann's constant. It's sometimes hard to measure the temperature. If you're putting a thermometer into a gas, it can melt or it can break in some way. But the point of this is that there's some things you can't measure, like the speed of a particular particle. And there's other things that you can measure that's easy to measure. It's the pressure, the volume, the temperature. And sometimes some combination of those are easier to measure. So the goal here is these are not necessarily supposed to be hard problems. They're, the homework that you're seeing here is mostly do the ratio sort of problems to solve for pressure, volume, or temperature, or do the kinetic energy problems. What's the energy of the gas? And the takeaway I want you to get from this is that the temperature is a function, the kinetic energy is related to the temperature. And because the temperature is a measure of the internal energy of the molecules. And that internal energy is going to cause the pressure that you see. So the pressure, the volume, and the temperature are all related. So this is not meant to be a super stressful chapter. This is meant to be something you should see. And when we start talking about sound and talking about waves in air, we're going to come back and revisit a bit some of this where stuff comes from. All right, so you'll notice, I don't know if you covered this in other chapters. If you look at the summaries for the chapters, there's a lot more stuff. We're not covering things like specific heats or distributions or adiabatic and other sorts of compressions and stuff. We're not covering thermodynamics. We're not trying to. Right? It just is basically limiting it to how do you deal with molecules that don't interact with each other other than collisions. Because that's a simple model we can build. And then, so what we're doing is as we go through our descriptions of stuff. All right, we started out at the very beginning of the year as playground physics, and we're shrinking it down to now we're talking about how individual molecules are interacting or not interacting. And all right, we're going to get eventually the goal is in a few weeks you'll deal with what are the individual particles in the molecules doing. What is and that's electricity and magnetism. All right, so this is not meant. This is a stepping stone. It's not meant to be difficult. This is meant to, make progress. So anyway, if you have questions, please email me. Please feel free to set up a jigsaw. I'm going to start teaching Radford next Tuesday, so I'll have a regular idea of what the schedule is. and I can make schedules for you if you need. If you want to meet every so often, that's fine. But the goal is when you need help, you ask for it, and I'll get it. Right. So let me know if anything comes up with the homework. Otherwise, science fair is coming up, so next video will be in some time.